This lecture is on the second half of section 2.1 in the text. We start with the dimension theorem. Let T be a linear transformation from V to W. If the dimension of V is finite, then the nullity of T plus the rank of T is equal to the dimension of V. You may have noticed that in the last three problems we did. Check back and look at them. The dimension of the null space plus the dimension of the range is equal to the dimension of V. So let's start out with supposing that the dimension of V is n and the dimension of the null space is k. So our goal will be then to show that the dimension of the range is equal to n minus k, or the rank. We're also supposing, since the dimension of the null space is k, we're going to start out with a basis for the null space. V1 through Vk is a basis for the null space. But we know from chapter 1 that we can extend this basis to a basis for the whole vector space V. So let's do that. We have V1 through V sub k is in our basis, and those are linearly independent vectors. They're a basis for the null space. So I'm going to extend with V sub k plus 1 up to vector V sub n and have a basis for V. So this set spans all of V, and it is linearly independent. Well, we know that the range is spanned. It's the span of T of V1 up to T of V sub n. That's what we had in previous theorem. If this is a basis for V, then we know that if we apply T to those vectors, that the range is the span of those vectors, but we don't know if they're linearly independent. In fact, we know, let me just stick in T of V sub k here. We know that these are all equal to 0, aren't they? So we know, in fact, that R of T is the span of just the vectors that we added in. V sub k plus 1 through V sub n. Because all of these were in the null space. So they just go to 0, and we don't need to have those in the spanning set. Excuse me, I made a big mistake here. We have to put T. Okay, make that change on your paper. So the range of T is spanned by T of V sub k plus 1 through T of V sub n. Now, we know that the span is true, but we need to prove that this set is linearly independent. Okay, so I erased and I put TP here to prove that set is linearly independent. We know that it spans the range. So to show that a set is linearly independent, we pick scalars a sub I from our field, and we say, suppose that a sub k plus 1, T of V sub k plus 1, plus down to a sub n, T of V sub n, is equal to the 0 vector, and that, of course, is the 0 vector in W. Well, T is linear, so this is the same thing as saying that T of a sub k plus 1 V sub k plus 1 plus a sub n V sub n is equal to the 0 vector in W. because T is linear. Well, if T sends this linear combination to the 0 vector, then that tells us that A sub k plus 1, V sub k plus 1, plus dot dot dot, plus A sub n, V sub n, is in the null space, because T sends it to 0. Okay, so if that is in the null space, we know that the set V1 through V sub k is a basis for the null space. So this must mean that there exists scalars, let's call them C1, C2 through C sub k, such that C1 V1 plus C2 V2 plus C sub k V sub k is equal to this that we said was in the null space. A sub k plus 1, V sub k plus 1, plus A sub n, V sub n. Well, if we subtract everything to one side, we have C1 V1 plus up to C sub k V sub k minus A sub k plus 1 V sub k plus 1 minus down to, finally, subtracting off A sub n, V sub n. And that is equal to the 0 vector in V. Well, the set V1 through V sub k plus 1, up to V sub n, that's a basis for V. So it is a linearly independent set. And if we have a linear combination of those vectors equaling the 0 vector, this implies to us that C1 is equal to C2 is equal to C sub k equal to A sub k plus 1 equal to all the way down to A sub n is equal to 0. Which tells us exactly what we wanted. We wanted A sub k plus 1 through A sub n to be equal to 0, to give us the fact that this set T sub V sub k plus 1 V sub T of V sub k plus 2, comma, dot, 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 T of V sub n is linearly independent. And therefore, we can say that the dimension of the range, which is equal to the rank, is n minus k. Therefore, the rank plus the nullity is equal to n. This theorem I am not going to prove. T is 1 to 1 if and only if the null space is the 0 vector. Well, we know this from group theory. The null space is the kernel of the mapping. So this would be exactly the same proof that we did before. We know V is an abelian group under addition, and we therefore know that T is 1 to 1 if and only if the null space or the kernel is the 0 vector only. Theorem 2.5, you could prove this yourself. It is very short little proofs. If the dimension of V is equal to the dimension of W, only if the dimensions are exactly the same, you can say that these three things are equivalent. Here we can say onto means 1 to 1. 1 to 1 means onto. It's just like if you have two sets containing 10 elements. If someone says you have a map from one set to the other and it's onto, well, you know it's 1 to 1, and vice versa. And we would say that the rank of T is equal to the dimension of V. Well, If T is 1 to 1 and onto, then the null space only contains the 0 vector, which means that it is dimension 0, and the rank would be n minus 0, the dimension of V. Here's a problem. We'll try to find the range and the null space, and therefore the rank and the nullity. We see that the dimension of V is 2. We know that the rank plus the nullity will be 2. One way you could do this is to know that the range R of T will be the span of whatever vectors we get by applying T to a basis for R2. So it would be T of, let's just use the standard basis. All right, so what does T of 0, 1 would be 1, 1. And I should have written span here. And T of 0, 1 is 1, 0. So we see these are linearly independent, and therefore this is a basis for the range, and we say that the rank is equal to 2, so the nullity is 0. Now, you could have just looked for the nullity first. You could have said, well, T sends A1, A2 to 0, 0 means that A1 plus A2 is equal to 0, and A1 is 0, which gives us A1 equals A2 equals 0. So we could see that the null space contains only the 0 vector, and therefore its dimension, the nullity, is 0, and the range and the rank would be 2 minus 0, or 2. So you can get the nullity or the rank either way. Here we have a linear transformation from the vector space of polynomials of degree less than or equal to 2 to R3, 3 space. And you see that it just is a coefficient vector. This transformation takes a polynomial and sends it to its triple of coefficients, the x squared, x, and constant. So I would like to see what the range, the dimension of the range, and I know it will be the span of, well, let's take the basis vectors for P2 of R. It's going to be the span of T of 1, T of x, and T of x squared. 1x and x squared is a basis for P2. And T of 1 is, well, that's going to be 0, 0, 1. T of x will be 0, 1, 0. And T of x squared will be 1, 0, 0. Well, we've seen that before. That's a linearly independent set, and in fact, it's just the standard basis vectors for R3. So this is linearly independent. The span of this set is all of R3, so we say that the range of T is really all of R3. The rank is equal to 3. T is 1 to 1, and it is onto. The dimension of these two spaces is exactly the same. And we know that the nullity is 0. The only vector that gets sent to 0, 0, 0 is the 0 polynomial. So since this linear transformation is 1 to 1 and onto, we could answer this following question by looking in R3 instead of the polynomial vector space. Let's say I asked if these three polynomials, 2 minus x plus 3x squared, x plus x squared, and 1 minus 2x squared, are linearly independent. Well, you could do it the way that we have been doing it and set up a linear equation, picking a coefficient a, b, and c, equating the coefficients, and making a matrix, row reducing it, and see if they are linearly independent. But since we have this one-to-one onto mapping, we could also just look at this set. 3, negative 1, 2, the coefficient vectors. And 1, 1, 0, and the coefficient vectors here are minus 2, the coefficient of x squared, 0, the coefficient of x, 1, the constant. So these are the images under T of those polynomials. We could ask, are these linearly independent? And so it's easier to answer that question. You could set up a linear equation, but I think by now you see what you're doing is just taking these and dropping them in a matrix as column vectors. And we want to know if, again, you don't have to put these zeros there. Okay, so now we would row reduce this, and I'm going to leave that up to you. If you have forgotten how to do this, you need to watch the video that I sent you by email, a short video on Khan Academy. What you would get would be, after 2 or 3 little, I came up with this. And I don't need to go any further. I mean, I could easily divide by 2 and get 1 here. And then adding, I could eliminate these two, but why go to the bother? We know now that they are linearly independent, because I got 1 here, 1 here, I can get 1 there, easily eliminate these two and make them zeros. So you have, if I had written this as a times this vector plus b times this vector plus c times this vector equals 0, 0, 0, then I now know that A equals B equals C, and we can say that the vectors are linearly independent. Okay, so we have another theorem here to prove, and one corollary, and then we're done with section 2.1. Theorem 2.6. Let V1 through V sub n be a basis for V, and let W1 through Wn be any vectors in W. They don't even have to be distinct, just any n vectors. There exists exactly one linear transformation T mapping V to W such that T of V sub I is equal to W sub I for I equals 1 through n. So, in other words, once you pick the images of the basis vectors, then that completely determines the linear transformation. What it does to the basis vectors determines uniquely what transformation it is. So this proof will have 2 parts. First of all, we have to prove that there exists a transformation, linear, that maps Vi to Wi, and then we have to show that that transformation is unique. So I'm going to define kind of the obvious transformation that would map the V sub i's to the W sub i's, and then we'll show it's linear. So for any V in V, since this is a basis for V, there exist scalars so that we can write V as a linear combination of its basis vectors. That's for any v in V. So here's how I'm going to define the mapping T. The one that we'll have to show is unique that does this. Let T map V to W by T of V is equal to A1 W1 plus A2 W2 plus A sub n W sub n. So literally we're just mapping the V sub i's to the W sub i's. All right, we have to show that this is linear. We will do both things at once this time. So we have to prove that T is linear. To show that T is linear, I will let C be in the field, and I'm going to let, excuse me, V be as I defined before, the sum from I equals 1 to n, A sub I, V sub I. And we need another vector in V. Let's call it U, and it will be the sum from I equals 1 to n of B sub I, V sub I. And we need to show that T of CV plus W, CV plus U, excuse me, is equal to C times T of V plus T of U. So I'm going to turn this off and just add these two vectors together to save time not recorded. As I just added CV and U together, and we get this. And T, we know what T does. What T does to any linear combination of the V sub i's, it just replaces the V sub i's with the vectors W sub I in W. So this will be equal to C1A1 plus B1 W1 plus, and replacing, the last one will be CA sub n plus B sub n times the vector W sub n. Now, you in your notes, you finish this off and see that you do get C T of V plus T of U. Therefore, T is linear. We've proven this. To prove that T is unique, we'll do the same thing we always do. Suppose that T of the V sub i's is equal to W sub I, and suppose there's another one. U of V sub I also gives us W sub I for I equals 1 through n. We want to show that T is the same as U on all vectors of V. So if we let V be an arbitrary vector in V, it would be A1 V1 plus down to A sub n V sub n, because that is a basis. And now let's just take U of V, and we want to show that we get T of V. U of V is, well, it's linear, so it's going to be A1 U of V1 plus down to A sub n U of V sub n. We're assuming that U is a linear transformation. And, oh, well, these are exactly the same as T. So it is A1 T of V1 plus, replacing the U's with T's, A sub n T of V sub n. And that is T of V. So we can say, therefore, U is equal to T, and T then, the one that we defined, is unique. So here's the last question. Let T map R2 to R2 by, well, this map right here. if U maps R2 to R2, and U of 1, 2 equals 3, 3, and U of the ordered pair 0, 3 equals 6, 0, prove U is equal to T. Well, the first thing we would want to do is make sure that T was the same, so let's compute T of 1, 2, and you see T of 1, 2 is 3, 3. Okay, so they're the same there, and let's compute T at 0, 3, and you see that it is 2a2, 6 minus 0 is 6, and 0. Okay, so we get the same thing. They act the same, but we can't say that they are the same linear transformation unless we know that the set containing 1, 2, and 0, 3 is a basis for R2. Well, clearly it is. One is not a multiple of the other. So this set is a basis for R2, and T and U act the same on each element of the basis. Therefore, we can say by the previous theorem that the mapping U is equal to the mapping T. In other words, every vector in R2 gets sent to the same image by U and T.